So in the previous video we have discussed about the linear independence of vectors, which was like if there are some vectors v1 v2 up to vn, and there are some constants, that is x1 x2 up to xn constants, or we can say that some variables which would be determined through n number of equations. If this combination, if we can get this equation only for if all the xi's are 0, then we can say that these vectors v1 v2 up to vn are linearly independent vectors, and all the vectors from the A matrices, whatever be the vectors, if those vectors are all linearly independent of each other by uh, by reduced row echelon form, we can have the A matrix as this. That is, all vectors will be, we can see very clearly that all the vectors v1 v2 up to vn are independent of each other, and all are pivotal columns, and these variables are pivotal variables. And for this combination to be linear, if there is any linearly independent linearly dependent vector, then this combination will hold, but there has to be at least a xi which is not equals to 0. And for that case we can understand the linear independence through an example. If, or first of all, we can recapitulate it like this, that if there is in a two dimensional case, if there are two vectors like this, then these two are linearly independent. But if there is vectors which are of like this, then these vectors are not linearly independent. They are all linearly dependent because these vectors are just scalar multiple of each other. Like we can say here that xn vn will be a scalar multiple of all the vectors except vn. And if this xi, at least one xi, is not equals to 0. So this is the basic concept of linear independence. And obviously all the basis vector in R2 are linearly independent. In R3 all the basis vectors are linearly independent. As we can see in a n-dimensional case, these are all the basis vectors, and these are all linearly independent vectors. So in case of this homogeneous equation, linearly independent for the system equation, for the matrix, all the vectors, column vectors of matrix A to be linearly independent, there will be only one solution of x, that is x1 x2 up to xn would be 0. All will be 0. The same thing, this equation, all would be 0. This is just described in equation form. So this is the concept of a linear independence. Now we will try to understand it with an example. let me okay, let me leave it just like that. We will try to understand it with an example. Say if A is a 3 cross 4 matrix, if A is A11, A12, A13, A14, A21, A22, A23, A24, A31, A32, A33, A34. If A is this, and if we can get the reduced row echelon form of A as this, if this is the reduced row echelon form of A, I'm sorry, if this is the, just a second, if this is the reduced row echelon form of A, say we have got this, say I'm just trying to generalize an example, not by putting any particular value. So if this is the reduced row echelon form of A, and by having this matrix we can see that these are two basis vectors. These vectors are linearly independent of each other, but we don't know about this one. But actually we can see that these two are not linearly independent of each other, and we will see it from this example. So the equation would be, there are four variables. The equation would be, you have to keep it in the screen to understand the equation. We can see the equation is, from this matrix vector multiplication we can see the equation is, let me take a dark color, x1 x2 dot 0, so x2 will not be there, b13 x3 plus b14 x4 is equal to 0, and there will be only one another equation, x2 plus b23 x3 plus b24 x4 is equal to 0. So this we are getting, these two equations we are getting from the original condition, the original equation of Ax is equal to 0, because this is A, this is A, this is A, this is X 0. One thing we has to know, and we already know, that A is equal to the reduced to echelon form of F. These matrices are same, so we can use this matrix or this matrix alternatively as per our need. So we have got these two equations from the original homogeneous equation of Ax is equal to 0. Now we can manipulate the equation in this way, these two equations in this way, x1 is equal to minus 3x3 b14 x4, and the second equation would be x2 is equal to minus b23 x3 minus b24 x4, these two equations. from these two equations we can see that if we take any value of x3 or x4, we can have many values on x1 x2. So actually we can see that we can write it down in this way: for infinite number of set of values of x3 and x4, we can get infinite number of set of values of x1 and x2. We can obviously see from these two equations. Now we can write that these equations in this way: x1 from the original equation ax is equal to 0, a11, a21, a31 plus x2, a12, a22, a32 plus x3, a13, a23, a33 plus x4, a14, a24, a34 is equal to 0. This is the equation, that is ax is equal to 0. Now if we put x3, say we are taking two sets of values for x3 and x4. x3 is equal to 0, x4 is equal to minus 2, and another set is x3, another set of values is x3 is equal to minus 2 and x4 is equal to 0. We can take infinite number of sets of values for x3 and x4. We are just taking these two and we will see what will be the value of x1 and x2. So x1 would be from these equations we can see, if we put x3 is equal to we have taken 0 and x4 is equal to minus 2. So from these two equations we can see that x1 would be, x3 is 0, so 0 minus 2 plus 2b14. So x1 would be 2b14, and for x3, for the same value x3 0 and x4 minus 2, we will get x2 as 2b24, x2 would be 2b24 for x3 is equal to 0, x4 is equal to minus 2, and for the second set of value, that is x3 is equal to minus 2 and x4 is equal to 0, we will get x1 is equal to will be 2b13 and x2 is equal to will be 2b23. x1 is equal to 2b13 and x2 is equal to will be 2b23 for x3 is equal to minus 2 and x4 is equal to 0. So we can have infinite number of solution, that is the for these two, for this value of x3 and x4, we will get x is equal to 2b1 4, 2b2 4, 0 minus 2. And for the second set of value, that is x is equal to minus 1 and x4 is equal to 0, we will have x as 2b1 3, 2b1 3, x2 will be 2b2 3, 2b2 3, and x3 is minus 2. We have already considered it, and x4 is equal to 0. So for any set of value, we will get a distinct set of x1 and x2, and for that we can have infinite number of x, that we have already written here. This is very important, very very important. So we can actually write for the equation, let me take a different color. For the equation, for the homogeneous equation, this, the trivial solution would be x1 is equal to x2 is equal to x3 is equal to x4 is equal to 0. For a fourth order system, obviously we are considering as a fourth order system. This would be the trivial solution. But for a non-trivial solution, that is if at least one of these are non-zero, then there at least one of these are non-zero, then there would be infinite number of solution for x1, x2, x3, x4. Okay, so this is the thing. We have almost covered the linear independence and the linear dependence. Now we can go to a related concept which is very much important in linear algebra, which is null space. Let me put a area here, which is null space. Null space. For a system of equations, say this equation, this homogeneous equation, Ax is equal to 0, the null space of A, the null space of A denoted by NA, is the solution of X. Solution of X means we can say if there is only one solution, so the span of the solution of X, we can write in a very clear term, solution of X. X is a vector, obviously. X is a vector. So we can see from the concept of a linear independence that if A is obviously as we have mentioned in the linear independence, that if A is a full rank, or all the column vectors of A, if A is full rank, we can write it again just for the better understanding. If if A is full rank, that means, or we can say all the column vectors of A are linearly independent, then null space of A would be only for this fourth order system would be the span of this. Span of this means the zero vector, only the center, the zero vector. So for a full rank matrix, the matrix of the null space of that matrix would be the zero vector only. Or Otherwise we can say, if a matrix, if the column vectors of the matrix are all linearly independent, then if that matrix transform a vector x, if that matrix transform a vector x to a zero vector, then the null space of that matrix would be zero vector. But from the same concept of linear independence, or rather from the concept of linear dependence, we can say, if a is not full rank, if a is not full rank, or a has one or more linearly dependent column vector, then Na would be zero vector. Na would be, obviously there would be the zero vector plus means in addition with that, and also some other vector, some other vectors, some other span of some other vectors. From this example we can see, we can find the span of these vectors. From this example, let me cut it and paste it on the page we are living right now. Sorry, okay, it's okay. Copy, paste. Okay. Okay. This is not necessary. Just copy it along with the thing. Okay. From this equation, we can write x1, x2, x4, x3 and x4 in a different way. x4, we can see it that x1 is minus x1 has a component of x3 and x4, and the coefficients are b1 3, and for x4 minus b1 3, as we have I've written, and that's for x4 is minus b1 4. Similarly for x2, x3 and x4 as components, that is, then the coefficients are minus b2 3 and minus b2 4. And for x3, it is x3 is equal to will be x3, so the coefficient will be 1, that is x3 is equal to 1 into x3, and x4 is equal to 1 multiplied by x4. But for x4 there is no component of x3, so that would be 0, and for x4 there is no component of x3, that would be 0, and for x4 the component, the coefficient of x4 would be 1, like that I've just shown here. Okay, so from these two we can obviously see that as there is two, as in the A matrix there is two linearly independent column, so we can have any set of number for x and x4, and for all the sets of number of x and x4 we can have infinite number of solution for x1, x2, x3, x4. So we can actually write this, and obviously this equation is coming from Ax is equal to 0, and we have to find the null space, that is the solution for x, and where x is this vector, x is this vector, we have to find the solution of this vector, so that we can show what is the null space of A. So here the null space of A, that is this, the solution of x1, x2, xn, x4, is the linear combination of these two vector. Is the linear combination of these two vector. So we can write that null space of A, or as I have mentioned earlier, that A matrix is same as the reduced row echelon form of A. So the null space of A, which would be equal to the null space of the reduced row echelon form of A would be the span of these two, span of just take a different color, span of this vector and minus b1 span of these two vector. Because as we can see that as these, all the solution of x is the linear combinations of these two vectors. So we can actually say that we can get x1, x2, we can get this vector, we can get this vector as the linear combination of these two. So the span of this one would be the span of the linear combination of this one, as we have studied earlier that span of any vector created by these two vectors, say there is these two are obviously these two are linearly independent vectors like these two, the linear combination of these two vectors can create infinite number of vectors in the R2. So all the vectors that can be created by these two, the span of all those vectors is R2, that is these two vectors linear combination span the whole R2. So the same thing here, that the span of these all the possible vectors which is the solution of x is the fall in the span of these two vectors. So this is the relation of null space and linear independence. So we can say that null space of A would be, as I've written, if A is not a full rank, that is A has one or more linearly dependent column vector, then null space of A would be 0 and also some other vectors. So 0 plus also all these infinite number of vectors. That is the span of these two vectors. In short, we can write. So we have learned the concepts of nullity along with the null space, along with the relation of null space with rank, and the rank and the linear independence of the column vectors of a matrix is same thing. So that's all, and next we will discuss some not some actually many other concepts of linear algebra, and also in this playlist obviously. So if you have any question regarding linear independence or span or null space of a matrix, you can really ask me in the comment section. So if you like this video and if you think that this video has helped you a lot, you can like, share, and please subscribe to my channel. Thank you.